this, and you can change that, and if you do this, if you do that. So I'm going to try and get away from that a little bit. So, you've seen about the kernels, you've seen about the data region, you've seen about if you've got a multi-loop loop nest, what sort of things can you play around with to try and get better performance? And then there's the more extreme stuff that goes around that may, for some people be important and some people not. But, what do you do when you've got a real application? Porting to a GPU, even with OpenACC, is not trivial. Where do you start? Somebody says, I've got this code, I want to port it. What do we do? What do you do on day one? You sit down. Where do you start? So what I'm going to go through is the exercise for another example code and this example code is a little bit more complicated, a bit more like a real application, but it's kind of small enough that we can still deal with it now. And just talk you through, and this is a very Cray-centric talk, I'm sorry, but if you're using Turdy, there are Cray tools and we're familiar with them. We like the Cray tools, we've worked hard on them, and I do urge you to use them. So the code that I was going to talk about was the NAS parallel one of the NAS parallel benchmark codes called the multi-grid code. It is another stencil code. So yes, I have talked about stencil codes quite a lot, mainly because it's trying to find out applications of the right size to use. And yes, stencil codes are particularly suited to OpenACC and GPUs because the parallelism is very explicit. But nonetheless, finite difference codes are used in a lot of scientific and engineering applications. So it's not so removed from the mainstream of what you might be doing. So the code, it's bigger than before. It's we're talking more like 1,000 lines rather than 200 lines. And the call tree is a lot more like the actual application. So in Practical 3, you get to play with this code. And so when you build the code, you make it, and then you run the code. You choose the problem size here. The default is B, and that's what you use for the practical. But if you want to change it, there's some things you can change there. And there are a bunch of other options that we'll talk about as and when. When you type make, there's a make file in the top level directory. That goes into another directory and uses that make file, which goes to get the architecture-dependent stuff from a third file. This is just the way the NAS parallel benchmarks work. I didn't rip all of that out. I kind of wanted to leave it as it is. So you compile the code for the CPU, you run it on one core, and then you look at what happens. Well, there's 3 important lines in the output. It tells you what the L2 norm is. Basically, this is the correctness check. And it says if this is right or not. Very important. Always check it says successful. And also always check that this has come out as a number and not a nan. I've had cases where it's come out as a nan and it still said it's successful. So check both lines. And it times itself and it converts this by some internal little sum into a performance figure. Big is better. So for the Fortran code, you get this result. For the C code, well, performance isn't quite as good. Why is that? The C is using dynamic arrays. I'm not sure that's helping. But I'm not too interested in that. Yes, of course, you can optimize that and see why the C code is slower. But for the point of view of this exercise, we're doing an OpenACC port. This is where we start, not where we end up. So the C code starts slightly slower coming out of the box. The first thing you want to do is learn about the application. Now, you can scroll through the code and you try and work out what calls what and what calls what. But sometimes the best thing to do is, because when you're doing that, there's a lot of routines. Which are the important ones? How do you kind of start to get a feel for the structure of the application? Well, profiling the code running on the CPU is a very good start. So this is a profile generated with the CrayPAT program, and the instructions for the practical let you generate such a profile yourself. You could use another there's lots of profilers around. CrayPAT is provided on the Cray systems, but there's gprof, there's whatever you could use. And then you look at this and it's telling you how much time is spent in each routine. So already, this is giving you a good feeling. These are the routines that take most of the time. So this is already giving you some idea about what routine, how many routines are important, how long do they take. The other routines might be important for the OpenACC port because of the data regions, but we'll worry about those in a minute. We'd like to try and understand how does data flow in our application. Well, one of the ways you can do that is by saying, well, what's the call tree? Which routine calls which routines and so on. So you can use CrayPAT to generate a call tree. So here what it's done is it is saying that the main program calls a routine called MG3P, just a bit indented there, and then this calls these 4 routines. But MG also calls the resid routine. So whereas in the previous profile it was saying resid took 54% of the profile time, actually it breaks it down here that you can see that resid is called in 2 different places in the code, both of which are taking about 27, 28% of the time. So you haven't had to look at the source code yet, but you're already getting some feeling for the structure. So this is always a good thing to do, to start with. Again, this code is quite small, so this is quite you can get this picture fairly easily, but it's a very good start with whatever code. But that was routine level profiling. Just because a routine takes a lot of time in the profile, that doesn't mean it's very suitable for putting on the GPU. What you really want to know is about loop nests. What loop nests are there in the code, and how much time did they take? Did this routine take a lot of time in the profile because it has one big loop nest, or did it take a lot of time in the profile because it had a lot of very small loop nests? This is relevant when you're trying to understand how to port the code. So a loop level profiling is very useful, and CrayPAT has this facility. You can compile with the Cray compiler with a special flag, and then when you profile, you can get a profile that's broken down by loops. And so here, again, other tools may also give you this information. This is what CrayPAT shows you. So it's telling me in the resid kernel, there is a loop at line 634 with 161, it was called 161 times. The number of loop trips per loop varied between 4 and 256. So this is a multi-grid code. It's doing coarse grids and fine grids, so it's not a surprise that we're seeing a variation in the trip counts. 4 is not good for a GPU port. That's too small. 256 is all right. What's the mean number? What's the average? Well, it's about 96. Okay. But then 634, then there's another loop at 635 and another loop at 636. If I look at the time spent in the loop at line 634 and the time spent in the loop at line 635, very similar. Those loops are perfectly nested. You can tell that. They're right next to each other in line number. The inclusive time is the same. Those are perfectly nested loops. This one was called 1,500 times. It had a mean trip count. It had between 4 and 256. The mean trip count was 201. So if you multiply together, now, so what's this number? If you multiply the number of times the outer loop was executed by the mean number of iterations for the outer loop, you'll find it's exactly the same as that number. Again, that's telling you they're perfectly nested. Within here, there's 2 more loops. One starts at 636 and one starts a bit later. If you look at the inclusive times, if you add them together, they're about the same as this. So I've got outer loop, and then within those, I've got 2 sequential inner loops. And you can see that structure for the program without looking at the code. So again, it's a good way to understand what's going on. The number of iterations here is very good information for your GPU port. So again, a profiling tool can give you that. Clearly, we should start with the resid kernel. You go in, you put it in. I'm not showing you the code, but you parallel loop. I might want to change the number of threads per block later, so I'll just put this in as a placeholder. I look at the arrays. There's these, because I've got 2 sequential inner loops. One uses a temporary array. One creates a temporary array that's used by the next. That temporary array should be private. The rest of the data, I look at the things. For C, it looks very similar. The difference is every time I'm moving an array here, I have to mention its size explicitly. Why do I have to do that when I didn't have to do it for Fortran? It's because with C, it's dynamic memory allocation, and a C array is just a pointer. A Fortran array is a funny little thing inside the compiler that tells it all about the size and shape of this data object. That information the compiler already has. For C, you have to give it that information yourself. But you just read it off from the loop trip counts. Again, you can see the source code in Practical 3, so I'm not showing source code here. We accelerate that one routine, and the code goes slower. But C actually goes slightly faster, probably because there was some poor scheduling going on in that loop on the CPU. But the Fortran is going slower. Why is it going slower? Well, you know the answer by now. It's data transfers. If you run it with runtime commentary, and you start looking every time I hit resid, I get all of this stuff. There's the resid kernel being launched. Before that, I've had some massive arrays being moved, and I've had some massive arrays coming back at the end. So I certainly know there's a lot of data. I know which arrays were responsible. If I use the Nvidia compute profiler, so I just run the code with this environment variable, I get an event-by-event commentary with timings. So it doesn't tell me, when it does a mem copy, what the array was called, but it does tell me how much time was taken. And you can see there's massive amounts of time here spent on transfers compared to the kernel. And for a more aggregated view, not just looking event by event, but to sort of see what's happening on the whole thing, CrayPAT, you can use CrayPAT to profile the OpenACC. And when you do that, what do you see? You see that data copies here are taking all the time, and that the actual kernel is taking an insignificant amount of time. Again, we're seeing sync waits tend to crop up quite a lot, because if everything's launched asynchronously, the time shows up in the waiting for the asynchronous events to finish. If you want to make the profile a bit easier to understand, you can tell it to not use the asynchronous launchings. So you recompile with this flag. And when you do that, you can also learn a bit more about how much data was transferred in each direction from the CrayPAT profile. And you can also do, if you so choose, you can do a profile where not only you look at the OpenACC, but you look at how the OpenACC kernels fit in with the CPU profile. And you can see that resid, this is the compute time. It's showing up in this async wait because that's when it finishes the kernel. That's slipped right down the profile, but what's gone right up the profile are the data copies associated with that routine. They're now the slowest thing going on. So what do we do? Well, at this stage, we just bite the bullet. We say, well, I know that data copies are a problem. I know that I'm going to have to get rid of those. I know that I'm going to need a data region. But a data region has to go around a number of kernels. So I need to port more kernels first. So psinv, this is an initialization routine, so it isn't in the main part of the compute. This one, psinv, rproj3, and interp, I need to get those ported across to the accelerator. So I do go in ACC, ACC, parallel loop, and the Fortran code is going even slower. Of course it is. It's now moving data for 4 different kernels, not 1. The C code is going slower, but wow, it's going particularly slow. At this stage, I've got a lot of the compute on the GPU. Why is it so much slower? You say to yourself. Well, that's when you go and you say, well, what did the compiler do? And so you look at you profile the code and you say, oh, the interp is very slow. What's going on in interp? You look at the compiler listing. Yep, big G, that's good. Partitioned this outer loop. Yep, that's good. Partitioned a vector loop here, that's good. Oh, no loop partitioning there. For some reason, it's worried that there are loop dependencies there. It's not partitioned that loop. So every thread is doing every loop iteration there. Bound to be slow. So we go in and we say, actually, these things are independent. So we put in this pragma, and when we put that pragma in, the C performance jumps right up to be pretty much bang on the Fortran performance, because it's doing the same GPU kernels, and it's doing the same data transfers. Not surprising. Now we want a data region. We want to go up the Calltree, put a data region in, make sure our arrays live on the GPU. Well, there's a few other kernels that we need to port first. There was that 0.3 kernel that you saw, and there were a few more at the less than 1% level, which are just tiny little copy kernels, but they've got to be on the GPU if the data is only going to live on the GPU. So you have to jump into those three, and you have to port those. When you do it, even slower. C, well, is that difference significant? It's kind of suspicious. So you go in and you look, and again, yeah, turns out in the COM3 there was another place where it wasn't vectorizing a loop. You correct that, and now, well, they're very close together. The main data arrays, U, V, and R, you can now call them create, because you initialize them on the GPU, you process them on the GPU, there's no data transfer at all. There's a couple of little parameter arrays which you copy in, but that's done right in the initialization, it's not important. And of course, in all of your kernels, if you'd said copy or create in the individual kernels, you now change it all to present, because you've got this outer data region. And that's when the performance jumps, because now the performance has gone from here to here, because you've got rid of the data transfers. And now this is impressive compared to that, whereas that was not. Again, in this case, Fortran and C very close together. And if you look at the runtime commentary and you grep out for all the copy lines, you find that the only arrays that are transferred are these little arrays right in the initialization. And everything else is just small internal copies that you have no control over and you can't remove. So we've checked the loop mark things for bad scheduling. We could try varying the vector length from the default of 128. So here's the 4 main kernels. Here's the time they take for different choices of threads per block. And so which is the lowest of the blue? Well, the lowest of the blue is kind of 128, 256, maybe 256 by a whisker. Red is best at 128. Green is best at maybe 64, but the effect is really tiny. Purple is maybe it's best there, but the effect is really tiny. So you can get about 5% on an individual kernel, but because some of them are already best around here, best around the default anyway, overall we only gain 2%. So we did really well with the Himeno code. With the multi-grid, there wasn't much to gain by varying the number of threads per block. Loop scheduling, we could do all the things we did before to try and look at the performance tuning. We could try blocking loops, we could try cache clauses. I've not done that here, but we could try avoiding the temporary arrays, what I said before. Sometimes having a temporary array, which might give you good cache usage, using a private scalar in the loop nest goes into registers better. You could rewrite the most expensive kernels in CUDA and then hand tune, but do remember, the compiler writers aren't stupid. So you don't necessarily, it's not a guaranteed win. I'm not saying you're not cleverer than them, but you know, I'm not cleverer than them. I just wrote a very simple CUDA version and managed to slow the code down. Not by much, but you know, it was better to use OpenACC. Avoiding the temporary arrays in resid, as I showed in the previous talk, that gave me a small speed up. But by far the biggest optimization is data movement. So how far did we get? Compared to a single core, we've done pretty well. We've got a factor of between 15 and 18 speed up. But what happens if you look at a full CPU or a full node? Well, on the XK7, if you use all the threads of the Interlagos and you do OpenMP, the performance does improve, but it doesn't improve to anything like this. We're still 2.6 times faster on the GPU. If I go across a full XE6 node, so if you say, I don't want to buy a GPU, I'll buy an extra CPU instead, when I run the OpenMP version of the code across all of those threads, the performance has improved with the second CPU. It's not doubled, of course. And we're still 1.5 times faster using the GPU. Is that good? Well, we don't expect to get 1,000 times. We might think, well, could we get 5 or 10 times? You know, is this good? It's not brilliant, but why wasn't it faster? The main reason is that this multi-grid application uses fine grids and coarse grids to solve the problem. Some of these coarse grids are 4-cubed, so you've got a 4-cubed loop nest being scheduled on the GPU. It's never going to run well. The CrayPAT loop profiling told us that we had really small loop nests sometimes. So then you start to say, well, why are we doing this? What was the point of multi-grid? The point of multi-grid was supposed to be an algorithm that enabled you to solve your problem faster on a computer by using large-scale information. So it was only ever an optimization. So perhaps when we think about this, maybe we need to think about our algorithm and say, well, actually for the GPU, going to a grid that's so coarse that it's a 4x4 grid wasn't a good optimization of my algorithm. Maybe I should have gone, stopped when I got to 8-cubed instead of going to 4-cubed. And if I do that, that will improve the performance. And that's where you, kind of as a scientist, or working with the application scientists, has to say, but did you really need to do this? Was there might have been an algorithmic reason why you thought that was an improvement, but maybe on this GPU, it isn't actually an improvement. But again, that's not something that I can answer. You need to know about what the science is, or the engineering, or whatever it is you're doing with your code to really know. So that was kind of a whistle-stop tour through the multi-grid code. I didn't show you the multi-grid code, and that was kind of deliberate because I kind of wanted to say, what can we do with tools to help us learn about the multi-grid code? So the idea of the final practical is that you take this code and you go through these stages of profiling the code on the CPU, of putting the OpenACC in, and of porting this code step by step and see how the performance changes. So we have a break now, but we've kind of lost a bit of practical time, but there is still time for some practicals. To go with this code, there is also a document, not just a set of slides, there's actually a document that kind of leads you through the process. The idea of that is to kind of, you can read that. You can almost read it without a computer because it kind of shows you the output as you go. But alternatively, you can read it as you go through this exercise. So we do have some time for practicals at the end still. So you can make a start on that. But again, it's the sort of thing that you can go away and read more at your leisure because it is more how you would approach your code. And this leads you through the stages of doing this. So if you look at, in the practical 3, there's again 2 directories, there's C and Fortran. Choose which you want. There's various versions of the code. There's more versions than there have been previously. Version 0, if you look in the subdirectory mg, you'll see mg_v00.f or .c. That's the original code, or very close to the original code as downloaded. No OpenACC. And then there's versions that incrementally go on from that. Version 1 is the same as version 0. The only difference is that sometimes when you're profiling the code, you don't want to profile the initialization stage. You want to profile the important compute stage. So it just shows you how you can switch the profiler on only for part of the code. So it just gives you an example of how you do that. There's no version 2. There used to be, but it was no longer necessary, so there's no version 2 anymore. Version 3 is where the first OpenACC kernel goes in the resid routine. Version 4 is where interp, rproj3, and psinv have also gained OpenACC acceleration. You can tell I spend too long with the code when I know the names of all the routines. That's version 4. Version 5, well, there were all these other norm2 u3 and all these other little routines that weren't important, but we still needed to port them. They've all got ported there. And at that stage, that's the really slow version of the code, version 5. Version 6 is where the data region goes in, and that's where the performance improves. Version 7 goes back to resid and says, oh, could we do a little bit of hand tuning here and maybe get it going a bit quicker? And then version 8 is where I say, oh, well, I'm going to use my wonderful CUDA kernel to replace the resid kernel entirely, but it goes a bit slower. It didn't on Fermi. Kepler is going worse. But, so those are the versions of the code that are there. So if you wanted to, say, well, what should I do if I accept that you can profile the code, but I just want to look at the OpenACC, well, look at version 3, which is where the first kernel goes in. Maybe try running that to get the runtime output. And then go maybe, if you want to look at the other ones, you can. Otherwise, dive straight into, say, version 6, which is where the data region's gone in. See where the data region's gone in. See which the different kernels are, how they've been, how you've changed the directives to present and this sort of thing. Run that. Again, look at what the output looks like. Profile that version. All of the instructions for how to do the profiling are in the document, which was in this directory. There was a p3 something.pdf. That gives you, it's quite a big document because it's designed to kind of be read and give a bit more information than just a set of bullet points. But it tells you the commands that you want to run in order to do this. You don't have to run the special makefile options. If you want to compile the code by hand, go ahead. There's no secret to it. But I've just made it a bit easier by automating some of this stuff to save a bit of time today. Were there any questions on that? As I say, I talk about CrayPAT, which is the Cray profiling tool. You have it available. You may as well make use of it. You're only learning about your application after all. There are, if you want to try other profiling tools, there are. Cray has worked quite hard to integrate so that you can get an integrated profile of GPU stuff, be it CUDA or OpenACC, and CPU stuff, and see it all in one profile. So, we think it's a useful tool. That's why we talk about it. But, it's not the only tool out there. And if you want to do things a different way, that's fine. There's one tool I've not talked about, which is a tool called Reveal. And there's a little bit more about that described in the document, but there wasn't really time to talk about that. It's a way of exploring your source code in a bit more detail without having to look through big text files and pull information from here and information from there. The stencil code. So yes, I have talked about stencil codes quite a lot, mainly because it's trying to find out applications of the right size to use. And yes, stencil codes are particularly suited to OpenACC and GPUs because the parallelism is very explicit. But nonetheless, finite difference codes are used in a lot of scientific and engineering applications. So it's not so removed from the mainstream of what you might be doing. So the code, it's bigger than before. It's we're talking more like 1,000 lines rather than 200 lines. And the Calltree is, what do we do? What do you do on day one? You sit down. Where do you start? So what I'm going to go through is the exercise for another example code of, and this example code is a little bit more complicated, a bit more like a real application, but it's kind of small enough that we can still deal with it now. And just talk you through, and this is a very Cray-centric talk, I'm sorry, but if you're using Turdy, there are Cray tools and we're familiar with them. We like the Cray tools, we've worked hard on them, and I do urge you to use them. So the code that I was going to talk about was the NAS parallel one of the NAS parallel benchmark codes called the multigrid code. It is a lot more like the actual application. So in Practical 3, you get to play with this code. And so when you build the code, you make it, and then you run the code. You choose the problem size here. The default is B, and that's what you use for the practical. But if you want to change it, there's some things you can change there. And there are a bunch of other options that we'll talk about as and when. When you type make, there's a make file in the top level directory. That goes into another directory and uses that make file, which goes to get the architecture dependent stuff from a third file. This is just the way the NAS parallel benchmarks work. I didn't rip all of that out. I kind of wanted to leave it as it is. So you compile the code for the CPU, you run it on one core, and then you look at what happens. Well, there's 3 important lines in the output. It tells you what the L2 norm is. Basically, this is the correctness check. And it says if this is right or not. Very important, always check it says successful, and also always check that this has come out as a number and not a nan. I've had cases where it's come out as a nan and it still said it's successful. So check both lines. And it gives you this, and you can change that, and if you do this, if you do that. So I'm going to try and get away from that a little bit. So, you've seen about the kernels, you've seen about the data region, you've seen about if you've got a multi-loop nest, what sort of things can you play around with to try and get better performance? And then there's the more extreme stuff that goes around that may, for some people be important and some people not. But, what do you do when you've got a real application? Porting to a GPU, even with OpenACC, is not trivial. Where do you start? Somebody says, I've got this code, I want to port it.